Hello, good evening everyone, and welcome to this week 3 tutorial of Applied Thermodynamics course. I am Thananka Sutia. I am a PhD student at the Center for Atmospheric and Oceanic Science at IISc Bangalore, and today basically we will be doing some sums, numericals that are related to the steam power cycle, but the ways that how we can increase basically the efficiency of that. That will be helpful for you to solve the questions uh, that are given in your assignment 3. So we'll wait for a couple of minutes and then we'll begin our class. Okay, so let us start today's class. So in today's class, basically we will be dealing with the ways how we can improve the efficiency of Rankine cycle. Okay, we have seen that the various components of Rankine cycle in the previous class. We have solved one or two problems related to each components, and also how to find the efficiency, the work done, the whatever things that we require to calculate in order to find the various things given in the question. So in today's class, we will be dealing the theory part is dealt by sir in the theoretical classes. So today I will be doing numericals, and along with the numericals only I will be telling you how you can basically improve the efficiency of a Rankine cycle. So and also in the last class I have given most of the values from the steam table. Today I will also be teaching you, although this is not a part of this course, but some of you may not have done this course, so quickly I will tell you how to look at the values if steam table values are not provided in the question, how you can extract the values from the steam table. Okay, so let us move to the first question then. So what it is telling us that a steam is generated at a power plant at 8 megapascal and 500 degrees Celsius is fed to a turbine. The exhaust from the turbine enters a condenser at 16 kilopascal, where it is condensed to a saturated liquid, which is then pumped to the boiler. Assuming a reversible adiabatic turbine operating at these conditions, you have to calculate the heat transfer to the boiler, the heat released from the condenser, the work done by the turbine, and the thermal efficiency of the cycle. Okay, so first of all, when you have to proceed all these questions, so the first part is basically you have to draw the schematic diagram. Okay, so we all know the schematic diagram of a steam turbine. Let me draw it once again. So there was the boiler component. Okay, then there was the turbine, and from the turbine exit there comes the condenser. Okay, and then from the condenser there was a pump. Okay, which basically transfers it to the boiler. Okay, this was our uh, schematic diagram, where this was the turbine, this was the condenser, and this was the pump. And if you remember that Wt amount of work is extracted and Wp amount of work is taken by the pump, and heat rejected is Q2, and then this heat taken is basically Q1. Okay, and if I name these things as all these points as this is point 1, this is point 2, this is point 3, and this is point 4, then my TS diagram becomes so these are the constant pressure lines. Okay, so my TS diagram becomes, if this is my point 1, and point from 1 to point 2 it comes. Okay, then this becomes my point 3, and this becomes my point 4. Okay, now this is what I have already taken as, but what is now is that we are not told in the question that whether the steam entering into the turbine that is this particular point, is it in this part or it is in this part. That means whether it is a saturated vapor or is it is a superheated steam, we don't know. Okay, so first of all, then let me write also these values. This is your 8 megapascal, and this is 0.016 megapascal. Basically I am converting all in megapascal because the steam table which I have, all the values are given in megapascal. Okay, so these two values are given to us. Now how can we first find out? So the first thing is, how can we find out that whether my point 1 is it dry saturated or is it superheated steam? Okay, so for that we have to go to the steam table. Now in the steam table there are basically three parts that you can see. One is the temperature based, the other is the pressure based, and the third part is the superheated or the saturated or the liquid part, superheated or the liquid water part. Okay, so first we will look through the pressure based, because here in our question, based on the pressure, we will see the value of this T saturation. Okay, this value is my T saturation value. Okay, at 8 megapascal I will check in the steam table what is my T saturation value. If my T saturation value is equal to 500 degrees Celsius, then my point will lie at this red dot. If my T saturation value is less than 500 degrees if my 500 degrees Celsius is greater than the T saturation value, then my this one point will lie inside this dome shape. And if my 500 degrees Celsius is greater than the T saturation value, then it will lie, the point will lie at outside. Okay, so let me write how to check whether point 1, that is entry to the turbine, is saturated steam or superheated steam. Okay, so so what we will go, yeah, so for the pressure based table we will go for 0.16 megapascal, sorry 8 megapascal. Okay, yes, you can see this is my 8 megapascal. This is my 8 megapascal. Okay, and for 8 megapascal what I have is that my T saturation is 295 degrees Celsius. Okay, these values are my T saturation values. Okay, so from steam table at 8 megapascal T saturation is equal to what? Is equal to 295 degrees Celsius. Now since 500 degrees Celsius is greater than T saturation at 8 megapascal, therefore point 1 is superheated steam. Okay, so now then what we will do, we will go to the superheated steam table, and there corresponding to 8 megapascal and 500 degrees Celsius, we will see the value of H, we will see the value of S, whatever we need. Okay, so let us go to the steam table now again. So this is the saturated part steam table. Okay, so now I will so I am here in the superheated steam table and I will go to 8 megapascal part. So this is the 8 megapascal, and at 8 megapascal and 500 degrees Celsius. okay, at 8 megapascal and my 500 degrees Celsius. These are my V values. Okay, this first column is basically my V values, and the second column is my U values, and the third column is my H, and the fourth column is my S. Okay, which you can also see from here. Okay, this first column is V, second column is U, third column is H, and fourth column is S. Okay, so at 500 degrees Celsius, so what we can write at 8 megapascal and 500 degrees Celsius, my H is equals to 3399.5 and my S is equal to 6.7266 kilojoule per kg Kelvin. Okay, in a similar way, the next pressure level is at 0.016 megapascal. Okay, we need to check for VF, we need to check for SF, we need to check for SG, we need to check for SF, and we need to check for HG. Okay, let us check it. And 0.16016 megapascal, and that we have to look at the combination of both, that is in based on the pressure based table. That is the first table which we have seen in today's class. So here it is. Look at this. So this is your T saturation. This is your VF. This is your VG. This is your UF. This is your UG. This is HF, HG, HFG, SF, SG, and SFG. Okay. So at 0.016 megapascal, what we need? VF. Okay, so what is VF? 0.0 0.001047 meter cube per kg. Okay, what is my SF? Your SF is 0.73664. Sorry, 0.77201. 0.77201 kilojoule per kg Kelvin. And your SG is 7.9846 kilojoule per kg Kelvin. HF is 231.67 kilojoule per kg, and HG is 2600.6 kilojoule per kg. Okay. So now look at here. So that means what is my H1 then? Therefore H1 is nothing. H at P equal to 8 megapascal, comma T equal to 500 degrees Celsius, which is nothing but this value, that is 3399.5 kilojoule per kg. Okay, similarly my S1 will be S at P equal to 8 megapascal and T equals to 500 degrees Celsius, that is nothing but this value, that is 6.7266 kilojoule per kg. Okay, now 1 to 2 is isentropic process. 1 to 2 is isentropic process. So therefore S1 is equal to S2. Okay, so this implies my S2 will be equal to what? 6.7266 kilojoule per kg. Okay, now S2 can also be written as SF plus X of Sg minus SF. Okay, so from here 6.7266 is equals to, what is my SF? Okay, SF at 0.016 megapascal, Sg at 0.016 megapascal, and SF at 0.016 megapascal. Okay, what is SF at 0. That is 0.77201 plus, I don't know what is my X2. Okay, 7.9846 minus 0.77201. Okay, so from here my quality of the steam at the exit of the turbine is 9846 minus 0.82. Okay, so this is basically the quality of the steam at the exit of the turbine. Okay, so from here then what can I calculate? I calculate H2. H2 is nothing but HF at 0.016 megapascal plus X2 plus X2 times Sg at 0.016 megapascal minus HF at 0.016 megapascal. Okay, so from here H2 is what? What is my HF? 231.67. X2 is my 0.82 times 2600.6 minus 231.67. So if you do this, your H2 will be equal to your H2 will be 2174 2174.1926 kilojoule per kg. So I have got H2. What is my H3 then at this point? This is nothing but the saturated liquid. Okay, so the saturated liquid at this point, so that means H3 is equal to HF HF at 0.016 megapascal. And what is my HF at 0.016 megapascal is 231.67 kilojoule per kg. Okay, then how to find H4? Okay, then how to find H4? So we know pump work is equal to what? Minus of VDP from P1 to P2, and in this case what it will be? VF at 0.016 times your 8 minus 0.016 into 10 to the power 3 kilojoule per kg. Why? Because the specific heat of specific volume of a liquid doesn't change too much if you even if you change the pressure. So from 0.016 to 8 megapascal, the if you look at the VF value, it won't change too much. Okay, so that's why you can take this VF as constant and you can take it out, and this can also be written as this can also be written as H4 minus H3 is equal to what is VF at 0.016 0.0010471 0.0010471 times 8 minus 0.016 into 10 to the power 3. Okay, so from here my H4 will be what? 231.67 plus 8.209264. So this one you will get at 239.879264 kilojoule per kg. So what are the values we have now? We have H4, we have H3, we have H2, and also we have H1. So we have got the enthalpies at all the points. So basically what we have to do, we have to calculate the enthalpies at all the points, then thereafter we can do all the different types of questions. Okay, so what is the first question? The heat transferred to the boiler. Okay. So heat transferred to the boiler. So what is my heat transfer to the boiler? If you apply the energy balance equation at the boiler, so let me check it once again. Suppose if this is my boiler, okay, so my inlet point is 0.1 and my outlet point is 0.4, I think. I'm sorry, I'm just writing the opposite case here. The inlet point was my 0.4 and my outlet point was my 0.1. Okay, so and Q amount of heat is done. So if you want to find heat transfer to the boiler Q1, that will be basically H1 minus H4. Okay, so if you do this, what is my H1? 3399.5 minus 239 239.879264 kilojoule per kg. So this is 3159.62 0.0736 kilojoule per kg. Okay, this is the heat transfer to the boiler. Similarly, heat released from the condenser will be what? Q2. Okay, and this Q2 will be nothing. It is H2 minus H3. Similar like the boiler. Okay, that will be basically H2 minus H3. What is the value of H2? 2174.1926. And what is H3? 231.67. So it is 1942.5226 kilojoule per kg. Okay. Next is what? Work done by the turbine. Work done by the turbine, that is WT. Okay, so what will be my WT? My WT will be nothing but H1 minus H2. H1 minus H2. So what is my H1? 3399.5. And what is my H2? 2174.1926. Okay. So it is 1225.3074 kilojoule per kg. Okay, and the last part is thermal efficiency of the cycle. Thermal efficiency, that is eta Th, is equals to W net by Q1. What is W net? It is basically Q1 minus Q2 upon Q1, and this can also be written as 1 minus Q2 by Q1. We have Q2, we have Q1, we put it here and we'll get. So what is my Q2? 1942.5226. And what is my Q1? 3159.6762736. Okay. So it is basically 38.52%. Okay, so this is how we basically calculate. So this is a general steam turbine question or steam power plant question. Now comes the next question, that they compare the thermal efficiency and quality of the steam at the exit of the turbine. If in this first question only, instead of 500 degrees Celsius, the steam is now superheated to 800 degrees Celsius. Okay, so that means what you are doing, you are superheating, or you are allowing the steam to enter the turbine at a much higher temperature than that when it was allowed to enter before. Okay, that means what is the role of superheating? So this question will basically tell us role of superheating at the turbine entry. Okay, so this question will basically compare the efficiencies of the two and the steam inlets also, that is the quality, that is basically the X2. Okay, so what are the things that will basically change? Let us see. Okay, I will only draw the TS diagram because we already know the schematic diagram of this one, so no need to waste time and draw it too much. So earlier if the point was somewhere here earlier, okay, now the point is somewhere here, that is 800 degrees Celsius. Okay, if this is my 500 degrees Celsius, okay, now this is basically so if so earlier the point was at 500 degrees Celsius, now my point number 1 is somewhere here. Okay, this is my point 1 now. Okay, so 1 to 2, 2 to 3 and then 3 to 4, and then this is 4 to 1. Okay, now my point is somewhere here. Okay, so and this point is nothing but my 800 degrees Celsius. The pressures are same. This pressure is my 8 megapascal and this pressure is my 0.016, and this pressure is my 0.016 megapascal. So what are the values at 0.016 megapascal? We already know. Let us write again that at 0.016 megapascal your Vf is 0.0010471, meter cube per kg. Okay. SF is 0.77201. kilojoule per kg Kelvin, and Sg is 7.9846 7.9846 kilojoule per kg Kelvin, and HF is I think 231.67 if I remember. Yes, 231.67 to 231.67 kilojoule per kg, and Hg Hg is equal to 2600.6 2600.6 kilojoule per kg. Okay, so this thing will remain the same because this one now, but here and we already know that the T saturation at 8 megapascal, T saturation is equals to 295 degrees Celsius. Okay, so therefore 1 is superheated steam. So from the superheated table now, what we have to go? We have to go to the 8 megapascal only, but now we have to look at the 800 degrees Celsius. Okay. Okay, so this is the 8 megapascal, and now we have to look at 800 degrees Celsius. Okay. Fine. So at 8 megapascal 8 megapascal and 800 degrees Celsius. My H my H is equals to 4123.8 and my S is equals to 7.5184 7.5184 kilojoule per kg Kelvin. Okay. So then what? Then the rest of the things are the same. So my H1 will be what? H1 will be H at 8 megapascal at 8 megapascal and 800 degrees Celsius. That is basically 4123.8 kilojoule per kg. And my S1 is S at 8 megapascal and 800 degrees Celsius, that is basically 7.5184 kilojoule per kg Kelvin. Okay. So again S2 will also be equal to my S1 and that is equals to 7.5184 kilojoule per kg Kelvin. And also S2 can also be written as SF at 0.016 megapascal plus X2 times Hg at 0.016 megapascal minus SF at 0.016 megapascal. Okay. So S2 is 7.5184, SF at 0.016 is 0.77201 plus X2 times Sg is 7.9846 minus 0.77201. Okay. So from here X2 is equals to 7.5184 minus 0.77201 by 7.9846 minus 0.77201. Okay. So this is equals to 0.93. Earlier in that question my that is X2 was equals to, it was less than this one. Okay, so I will make a compare at the last part. Now let me first calculate everything whatever I am doing. So H2 is equals to HF at 0.016 megapascal plus X2 times Hg at 0.016 megapascal minus HF at 0.016 megapascal. Oh, I'm sorry for that. Okay, so and from here HF is 231.67 plus 0.93 times Hg 2600.6 minus 231.67. Okay. And so this will be 2434.7749 kilojoule per kg. Now my H3 will again be the same, that is HF at 0.016 megapascal, which is nothing but 231.67 kilojoule per kg, and also my H4 will also be the same because the pressure will also be the same, the Vf will also be the same. So whatever H4 I have got in question number 1, that will be the same here. So that is 239.879. 239.879 kilojoule per kg. Okay. So I have got again all the points. So now I have to calculate what I have to compare. I have to compare the thermal efficiency, and I have to compare the quality of the steam at the exit. Okay. So first of all, let me check the thermal efficiency. So thermal efficiency will be equals to 1 minus Q2 upon Q1. Okay. So what is Q2? 1 minus Q2 is basically H2 minus H3, H2 minus H3, and my Q1 is H1 minus H4, H1 minus H4. Okay. H2 minus H3 will be 2434.7749 minus 231.67. Double to 03.1049, and my Q1 is H1 4123.8 minus 239.879 double 3 sorry 3883.921. So this is equals to your 43.27%. So therefore, compared to question 1, number 1, quality of the steam is improved. Okay, so earlier we got 0.82 and now we got 0.93. So quality of the steam is improved at turbine exit. Okay, and also efficiency of the cycle is improved. So what we can conclude? So conclusion is that number 1, superheating the steam at the entry of the turbine improves quality of the steam at the exit of the turbine, and number 2, improves the efficiency of the cycle. Okay. So these are basically the two conclusions, that if you basically superheat, so quality of the steam is improved. So if the quality of the steam is improved, that means the erosion of the turbine blades will not happen as compared to the previous case. Okay, and the second case is that your efficiency of the cycle is improved. Okay, next part is the third question. So compared to the question number 1, the thermal efficiency and the quality, the same thing. Thermal efficiency and quality of the steam at the exit of the turbine, we have to compare it compared to question number 1. If instead of 8 megapascal, now my boiler pressure is 15 megapascal, okay, and the inlet temperature is same, 500 degrees Celsius or so, okay. So what is now so now this is what my 15 megapascal, and this is the same as 0.016 megapascal, okay. And now this temperature, this 0.1, it is 500 degrees Celsius, okay. And this is 0.2, this is 0.3 okay, this is 0.2, this is 0.3, and this is 0.4, okay. Again, at 15 megapascal we will now check what is my T saturation, and of course it will be at this point only. Still, let me check it here. So it's 8, 9, 10, 11 15. So at 15 megapascal my T saturation is 342 degrees Celsius, okay. So at 15 megapascal T saturation is equals to 342 degrees Celsius. So therefore 1 is superheated steam, okay. So superheated steam is now entering the turbine, okay. So therefore at 15 megapascal and 500 degrees Celsius, what we have to take, we have to take H and we have to take S, okay. So this is my 500 degrees Celsius, and this is my H value, and this is my S value, okay. My H is 3310.8 kilojoule per kg, and my S is 6.3480 kilojoule per kg Kelvin, okay. Okay, and again we also know these values. At 0.016 megapascal my Vf is 0.00100471 meter cube per kg. Sf is equals to 0.77201 kilojoule per kg Kelvin. My Sg is equal to 7.9846 kilojoule per kg Kelvin. My Hf is 231.67 kilojoule per kg, and my Hg is 2600.6 kilojoule per kg, okay. So therefore H1 is nothing but H at 15 megapascal and 500 degrees Celsius, that is equal to my 3310.8 kilojoule per kg, and my S1 is nothing but S at 15 megapascal and 500 degrees Celsius, that is 6.3480 kilojoule per kg Kelvin, okay. So again S2 is equals to S1 is equals to 6.3480 kilojoule per kg Kelvin, And from here S2 is equals to SF at 0.016 megapascal plus X2 times Sg at 0.016 megapascal minus SF at 0.016 megapascal. Okay, so S2 is 6.3480, SF is 0.77201 plus X2 times 7.9846 minus 0.77201. Okay, so from here your X2 is equals to 6.3480 minus 0.77201 by 7.9846 minus 0.77201. Okay, so this is your 0.77. Okay, so this is the quality of the steam at the exit of the turbine. So remember, in question number 1 the quality of the steam was 0.82 and now it is reduced to 0.77. so when you increase the boiler pressure, the quality of the steam gets degraded. Okay. So then we can calculate H2, that is nothing but HF at 0.016 megapascal plus X2 times Hg at 0.016 megapascal minus HF at 0.016 megapascal. So 231.67 plus 0.77 times 2600.6 minus 231.67. Okay. So that is equal to your 2055.7461 kilojoule per kg. Okay, similarly my H3 will be equals to HF at 0.016 megapascal, that is nothing but your 231.67 kilojoule per kg, and H4 will be similar to that in case of the question number 1. I will not do the same calculation again. So my H4 will be 239.879 239.879 kilojoule per kg. Okay, so now eta thermal will be equal to 1 minus Q2 by Q1. And what is Q2? Q2 is nothing but H2 minus H3, 1 minus H2 minus H3 divided by H1 minus H4. Okay, H2 minus H3 is 2055.7461 minus 231.67. so this is 1824.0761, and H1 minus H4 H1 is your 3310.8 and H4 is 239.879. okay, so this is 3070.921. okay, 1824.0761 by 3070.921. okay, so your efficiency is 40.60%. so therefore compared to question number 1, efficiency increased, but what is the problem is there, that the quality of the steam at the turbine exit is decreased. Okay. So what are the conclusions then? Conclusions. Next, if we increase the boiler pressure, then what happens? Number one, efficiency of the cycle increases, but the quality of steam at turbine exit decreases. Okay, fine. So that means the two ways, these are the first two ways by which we can increase the efficiency of a Rankine cycle. One, by superheating the steam before it enters the turbine, and by two, by increasing the boiler pressure. Okay, so both we have seen, and there are advantages and disadvantages which I will discuss in the last part of this today's class. So next, let us move on to the third part by which we can increase the efficiency of a Rankine cycle, and that is by performing some reheating is performed. Okay, so what is this reheat? So we will do one question and then we will understand what is this, how is this reheat cycle is actually looks like. Okay, so consider a steam power plant operating on an ideal reheat Rankine cycle. Steam enters high pressure turbine at 15 megapascal and 600 degrees Celsius and is condensed in the condenser at a pressure of 10 kilopascal. Now, if the moisture content at the steam exit at the low pressure turbine is not to exceed 10.4%, then determine the pressure at which the steam is to be reheated, and then the thermal efficiency of the cycle. Assume that the steam is reheated to the inlet temperature of the high pressure turbine. Okay, so what it will do in case of reheat cycle. Okay, so reheat Rankine cycle. Okay. So this was my boiler, suppose. Okay, and this is my turbine. So in reheat, what happens, that after it comes out, it is again reheated through the boiler. Okay, and again it is passed to another turbine. Okay, and then it is allowed to pass through the condenser, and then by means of the pump, this basically goes here. Okay, so this we name it as high pressure turbine, and this we name it as low pressure turbine. So there will be two turbine blocks now. This will be WT1 and this will be WT2. Okay, so this will be my WP, this will be my Q2, and this will be my Q1. Okay. Fine. So if I name this point as point 1, this is point 2, this is point 3, and then this is point 4, and this is point 5, and this is point 6. Okay, so how will my TS diagram then look? So say this is my P boiler. Okay, so that means the P1, and what it will do, that from point 1 to point some intermediate pressure, this will basically expand. Okay, and after this expansion, this is again reheated. Okay, this is again reheated. Okay, and it is reheated to the same temperature in our question. Okay, so this is my point 2 and this is my point 3, and then from this point 3 now this is expanded. Okay, so this point 3 now this is expanded to point 4. Okay, suppose this is my point 4, and then this is the point 5, and then from point 5 to this is my point 6. Okay, is it clear? This is how basically your reheat cycle will work. So what we do, so our main idea is to increase the mean temperature of heat addition. So what we do, we first of all expand from point 1 to point 2 in a turbine, in that high pressure turbine, and from there we again reheat by passing it through the boiler. Okay, there are some special arrangements of reheating, and after that we will be reheating to back again to the same temperature as that it was there in case of the your point 1. Okay, so your here T1 is equals to T3. Okay, then back again from that another that low pressure is achieved. So from that low pressure now it is again expanded to, if this is let me use some other colors for the pressures. So if this is my P1, this is my P2, so let me name this as ABC. This is PA, this is PB, and this is my PC. Okay, so from PB to PC is now it is again coming it back. So what are the things that are given to us in this question now? In this question, your PA is equal to 15 megapascal, and we have already seen that in 15 megapascal the saturation temperature is less than 600 degrees Celsius. So whatever steam is entering is a superheated steam. So we know T1, and that T1 is 600 degrees Celsius. Okay, then what we know the condenser pressure, that is my PB, or that is my P4, PC. Okay, PC is 10 kilopascal, and this I can also write this one as 0.010 0.01 megapascal. Okay, and this T1 is also equal to T3. How? Because we are assuming that the steam is reheated to the inlet temperature of the high pressure turbine. Okay, and one more thing it is given to us, that at this point, that is the point number 4, the moisture content of the steam at the exit of the low pressure turbine is not to exceed 10.4%. Okay, so that means your X4 is given as 1 minus 10.4 divided by 100. Okay, 0.896. Okay, so this is the moisture content. So then what we have to look, that what are the enthalpies values we know. Okay, so at 15 megapascal and 600 degrees Celsius. Okay, we will look at the steam table. So okay, I think these values I already have, because oh no, for 800 degrees Celsius we have done, 500 degrees Celsius we have done. So at 15 megapascal and 600 degrees Celsius. Okay, so your H value is 3583.1, H is equals to 3583.1 kilojoule per kg, and your S value is 6.34 6.3480 kilojoule per kg Kelvin. Okay. No, it is 6.6796. Sorry, it is 6.6796 kilojoule per kg Kelvin. Okay, and then at 0.01 megapascal, you will look at the table. I am just writing the values. Vf will be equal to 0.01027 meter cube per kg. Okay. Sf will be equal to 0.64920 kilojoule per kg Kelvin, and Sg will be equal to 8.14886 kilojoule per kg Kelvin. Okay, and your Hf will be equal to 191.81 kilojoule per kg, and Hg is equal to 2587.9 kilojoule per kg. Okay, so these are the values that we know from this steam table. So now what we can write is this: H1 is nothing but H at 15 megapascal and 600 degrees Celsius, which is nothing but 3583.1 kilojoule per kg. Okay, and your S1 is equals to S at 15 megapascal and 600 degrees Celsius, which is equals to 6.6796 kilojoule per kg. Okay. Then what we know, S1 is equal to your S2 is equal to your 6.6796 kilojoule per kg. Okay, we also know X4. Okay, so X4 is what? 0.896. so from here what we know, H4 is nothing but Hf at 0.01 megapascal plus X4 times Hg at 0.01 megapascal minus Hf at 0.01 megapascal. Okay, so what is Hf? That is 191.81 plus X4 is 0.896, and Hg is 2587.9 minus 191.81. Okay, if you put this, what you will get? 0.896 into 2587.9 minus 191.81 plus 191.81. Okay, so this is equals to 238.70664 kilojoule per kg. This is your H4. Similarly, I know S4. Okay, S4 is what? Sf at 0.01 megapascal plus X4 times Sg at 0.01 megapascal minus SF at 0.01 megapascal. Okay, so SF 0.64920 plus 0.896 into 8.14886 minus 0.64 0.64920. Okay. 7.36 7.3688 kilojoule per kg Kelvin. Now see, we don't know the intermediate pressure, so and again what we know that S3 will be equal to S4, and that is equal to 7.3688 kilojoule per kg Kelvin. So at point 3 now we have two values. One is the entropy value and the second is the temperature value. So we will look at the steam table. Okay, so in order to find the intermediate pressure, what we will do, to find PB, okay, we will look at the steam table where S steam table and find the pressure level where my S is equals to S3 and my T is equals to T3. Okay, so this will give us the reheat pressure. So you go and look at the steam table. What you will get actually, you will get PB is equals to 4 megapascal. Okay, so at 4 megapascal you will basically get these things. Okay, so therefore then what I can find out, so the point 3 now I have these values. Okay, that 4 megapascal. Okay, so this value I have. So what I can do is that at 4 megapascal and at 4 megapascal and what is the temperature? The temperature is 600 degrees Celsius. 600 degrees Celsius. I need to look for the H. Okay, and this will be equal to my H3 value. Okay, so you look at this 4 megapascal. Yes, at 4 megapascal and 600 degrees Celsius your H is 3674.9. okay, so it is 3674.9 kilojoule per kg. Okay, so this is equals to your H3. Now then what is required for us? The pressure at which the steam is to be reheated, this is equals to 4 megapascal, we have find out. And then the thermal efficiency of the cycle. Okay, so for the thermal efficiency, again let us find all other things. So what are the points we have got? H1 we have got. Okay, we have got H1. Have we got H2? No, we have not got H2. So how we can calculate H2? First of all, let us check whether we need H2 or not. So to find the thermal efficiency of the cycle, so eta thermal will be equal to what? 1 minus Q2 by Q1. And what is Q2? 1 minus this will be H4 minus H5, H4 minus H5, and that will be your H1 minus H6. Okay, so we don't need the value to find this one. So if you have to find out the turbine work, then you can do that. Okay, so yes, similarly you can do that. Now what is H4? We have already got. So what is H5? Your H5 is HF at 0.01 megapascal. Okay, and what is HF? At 0.01 megapascal, it is 191.81 megapascal. Okay, so then how we can find H6? So H6 minus H5 is equals to VF at this point 0.00101027, 0.00101027 0.00101027, okay, into 15 minus 0.01 into 10 to the power 3. Okay, so from here H6 will be equal to 191.81. So this is equal to your 206.953 kilojoule per kg. Okay, so just put it here. So eta thermal will be 1 minus H4 is 2338.2338.2 338.70664 70664 minus H4 minus H5 191.81 divided by H1. What is your H1? 3583.1 3583.1 minus 206.953. Okay, so this will be your 36.4%. Okay, fine. Then let us move to the next question. That okay, now we have studied reheat cycle. Now the next thing is, like, we can also do regeneration. Like if we do not want that we want to reheat the steam that enters the before the turbine, we can also do one thing, that we can take out some amount of steam, or we can allow the feed water of the boiler to heat before it enters the boiler. Okay, so what we can do is that okay, so we know that from here to here this much amount of heat we need to give. What if we can decrease this part? Okay, so that our Q1 will be decreased, and if we decrease the Q1, then our input value will decrease compared to the same output. So in this case our efficiency will so this can be done by means of regeneration. So in order to understand how this regeneration work, we will just solve one question, like prove the efficiency of an ideal regenerative cycle is equal to that of the Carnot cycle. So first of all, let me draw once again the schematic diagram of your ideal regenerative cycle. Okay, Yes. So this is my boiler, and from my boiler it enters the turbine. Okay, and from the turbine now this enters the condenser. Okay, and from the condenser now it enters the pump. Okay, now but before going to the boiler directly, what you will do, you will allow to pass through the turbine so that the hot steam will come this side, and the condensed water will come this side, and in doing so the condensed water will automatically get heated. So basically a heat exchange will take place, and then it will enter the boiler. Okay, so this is how an ideal regenerative cycle works. Okay, this is turbine, this is so this is how an ideal regenerative cycle works. Ideal regenerative cycle. Okay, so if I name this point 3, this point 4, this point 1, this point 2, then this point will be 2 prime. Okay, so then let me draw the TS diagram of this one. TS okay, so in the earlier case, if this was my point 2, this was my point 3, then this would have been my point 4. Okay, and this would have been my point 1. Okay, this was my earlier case, that if I would not have performed any type of regeneration. Now if I have performed the regeneration, what happens is that my this point 3, from point 3 I am no more expanding it, rather than there will be some amount of cooling of this thing. Okay, at this particular pressure. Okay, there will be some amount of cooling, so this will be coming back to here 3 prime. Let me change the color. Okay, so now instead of my what you call instead of heating it from 2 to 3, now the boiler is basically heating from 2 prime to 3 prime. Okay, and instead of releasing heat from 4 to 1, now my boiler is releasing heat from 4 prime to 1. Okay, so what it does, so from here the assumption is what? Assumption is that the heat gained by feed water is equal to heat lost by the steam at the turbine. Okay, so this will lead to your, therefore my T2 is basically equal to my T3 prime. Okay, and T2 prime is equal to my T3. Okay, so therefore change in entropy of water, and remember this one I am considering this as reversible process because this is an ideal regenerative cycle. Okay, and that must be equal to your heat released by the steam. Okay, so therefore delta S water, change in entropy of water, must be equal to change in entropy of the stream. Okay, fine. So what I can write is says, therefore what is the change in entropy of the water? The change in entropy of the water is S1 prime minus S1. Okay, and that must be equals to your S4 minus S4 prime, and this I can rewrite this as S4 minus S1 prime, and that is equals to your S4 prime minus S1. Okay, again S4 minus S1 prime is also equals to what? S2 minus S3. S3 minus S3 minus S2 prime. Okay, so now therefore eta thermal will be equal to what? 1 minus Q2 by Q1. What is Q2? Q2 is basically the heat rejection. Okay, and heat rejection is from point 4 prime to 1. Okay, so this is Q2 is the this process is from 4 prime to 1. Okay, let me write it here. Q2, this Q2 is 4 prime to 1 process. Okay, so this Q2 will be now equal to what? T, if I am naming this as this temperature as TL and this temperature as TH. Okay, so this will be TL times S4 prime minus S1. Okay, similarly my Q1, now Q1 will be equal to what? And this Q1 is nothing but the process from 2 prime to 3. Okay, so this process, so this will be T high of S3 minus S2 prime. Okay, so therefore eta thermal will be equal to what? 1 minus Q2 by Q1, that will be 1 minus T L times S4 prime minus S1 divided by TH times S3 minus S2 prime. Now we have already known from this equation that S4 minus S1 prime is nothing but S3 minus S2 prime, so these two will get cancel each other. So finally what we get is that eta thermal is equal to 1 minus TL by TH, and this is nothing but equals to, if you run any Carnot cycle between these two temperature, so this two temperature reservoir, high and low temperature reservoir, this will be equal to the same as that if you run any Carnot cycle. Okay, so an ideal, therefore the efficiency of an ideal regenerative cycle is equal to that of Carnot cycle. Okay, fine. Now there are some drawbacks in case of ideal regenerative cycle. What is the drawback here? You see here in the schematic diagram, we allow the feed water that is coming from the pump to enter into the steam turbine, and we know that steam turbine cannot deal with liquid or that two-phase mixture. So if there will be more liquid content, there will be erosion of the blades. Yes or no? There will be erosion of the turbine blades. So in order to protect that, we don't allow the feed water to heat this way. What we do, we use feed water heaters. Okay, we will do this thing externally, that, and by doing this next question you'll understand how this basically happens. So consider a steam power plant that operates on a regenerative Rankine cycle, and a net power output of 150 megawatt is produced. Now steam enters the turbine at 10 megapascal, 500 degrees Celsius, and condenser at 16 kilopascal. The steam is extracted from the turbine at 0.5 megapascal to heat the feed water in an open feed water heater, and then water leaves the feed water heater as a saturated liquid. Now determine the mass flow rate of the steam trolley boiler and then thermal efficiency of the cycle. Okay. Yes. So how we do this? So first of all, let me draw this one is the boiler. Okay, then this one is the turbine. Okay, what we do, that we extract some amount of mass that is going from here. Okay, then this is allowed to pass through the condenser. Okay, from the condenser this comes to pump 1. Okay, and this pump 1, this will allow to mix at this feed water, and this feed water, if it is a closed feed water heater, but in this case it is an open feed water heater. So already sir told you, I think, the difference between the open and closed feed water heater. In closed feed water heater the two liquids does not get mixed, but in open feed water heater the two liquids get mixed. Okay, so in this case the liquid will get mixed. What we do, we basically take out some amount of mass, say x dot amount of mass from that part. Okay, what we do, we take out some x dot amount of mass from whatever mass is flowing through the turbine, and then we take it and mix it, and finally the mass. Then after that what happens, by means of this pump, it is again going back to this boiler. Okay, this is how the overall process looks like. Now if I name these points, if this is my point 1, say this is my point 2 at which I am extracting, then this is my point 3, this is my point 4, this is my point 5. Okay, this is my point 6, this is my point 7. Okay, so in this case, if I am taking m dot amount of mass is coming here, so from here now it will come m dot minus x dot amount of mass. Okay, here also it will be m dot minus x dot amount of mass, here also it will be m dot minus x dot amount of mass. Now this m dot minus x dot mass, this mixed up, and it again becomes here m dot amount of mass, m dot amount of mass. So this is how the mass balance takes place. Okay, and if you want to look at the TS diagram, okay, so you look at the TS diagram. Okay, so what we do, we take this point mass. Okay, and this is my point 2, so till here, and then this is my point 3, this is my point 4. Okay, this is my point 5, this is my point 6, and this is my point 7. Okay, now remember, if we would have directly pumped from point 4 to point 7, then we would have been somewhere here, and then this much amount of heat, this from here to here we had to put a heat. So now this heat input is basically getting reduced. So this is the use of the regenerative cycle. Okay, if you are getting what I'm trying to say. Okay, so now let me again draw the similar way the mass. Here m dot amount of mass is coming, then here x dot amount of mass is getting extracted, so here m dot minus x dot amount of mass is coming, here also m dot minus x dot amount of mass is coming, and then finally here m dot amount of mass is again going from here. Okay, so these are all the points that are given to us. Okay, so then what it is given to us, that net power produced is equal to 150 megawatt. Okay, and then T1, that is at the point 1, that is inlet to the turbine, is basically given to us as 500 degrees Celsius. Okay, and then this is given to us as what it is given to us, this is given as 10 megapascal, and this condenser pressure is given to us as 0.016. okay, this is given to us as 0.016 megapascal, and this is given to us as 0.5 megapascal. Okay. So now from steam table, at 500 degrees Celsius and 10 megapascal, H is equal to 3375.1 kilojoule per kg, and S is equals to 6.5995 kilojoule per kg Kelvin. Okay. At 0.5 megapascal, Vf is equal to 0.00109 meter cube per kg. Hf is equal to 640.09 kilojoule per kg, and Hg is equal to 2748.1 kilojoule per kg. Okay. Sf is given as 1.8604 kilojoule per kg Kelvin, and Sg is 6.8207 kilojoule per kg Kelvin. And again at 0.016 megapascal, Vf is given as 0.0010471 meter cube per kg. Sf is equals to 0.77201 kilojoule per kg Kelvin. Sg is equal to 7.9846 kilojoule per kg Kelvin. Hf is equal to 231.67 kilojoule per kg, and Hg is equal to 2600.6 kilojoule per kg. Okay. So therefore H1 is equal to H at 500 degrees Celsius and 10 megapascal, that is nothing but 3375.1 kilojoule per kg, and S1 is S at 500 degrees Celsius and 10 megapascal, and that is equal to 6.995 kilojoule per kg Kelvin. Now I have directly written this point 2 inside this dome, but I may be wrong also, because whenever I am extracting, I may be extracting a superheated steam or a saturated steam. Okay, so note here we don't know that the extracted steam is superheated or saturated. Okay, so this one first we have to check. So how will we check? We know that S2 is equal to S1, and that is equal to your 6.59 6.5995. $6.5995 kilojoule per kg Kelvin. Now at the intermediate pressures 0.5, we need to check SF and SG, and if my this S2 lies between SF and SG corresponding to 0.5 megapascal, then it is in this dome, otherwise it is outside this dome. Okay, so since S2 no what I can write is that since SF at 0.5 megapascal is less than S2, and this is also less than Sg at 0.5 megapascal, therefore the extracted steam is saturated steam. Okay, these are the things that you should be careful, otherwise you have to look at the superheated table. You will not even find these values. Okay, fine. So then let us find the x2 value. How can find the x2 value? So we know that S2 is equals to SF at 0.5 megapascal plus x2 times Sg at 0.5 megapascal minus SF at 0.5 megapascal, and from this you just put here and you'll get x2 is equals to 0.95. Okay. Then we can calculate H2. H2 is nothing but HF at 0.95 megapascal plus x2 times HG at 0.95 0.5 megapascal 0.5 megapascal minus HF at 0.5 megapascal. So from here H2 will be what? HF at 0.5 megapascal is 640.09 plus 0.95 times 2748.1 minus 640.09, and this will give you H2 is equals to 2642.6995 kilojoule per kg. Okay. Then S3 is also equals to S1, and that is equals to 6.5995 kilojoule per kg Kelvin. So, and S3 is equals to SF at 0.016 megapascal plus X3 times Sg at 0.016 megapascal minus SF at 0.016 megapascal, and from this what we can find X3 is equals to 0.81. Okay, and then from here H3 will be equal to what? HF at 0.016 megapascal plus X3 times Hg at 0.016 megapascal minus HF at 0.016 megapascal, which will give you H3 is equal to 2150.5033 kilojoule per kg. Okay, and then H4 is nothing but HF at 0.016 megapascal, and this will be your 231.67 kilojoule per kg. Okay, then similarly H5 minus H4 will be equal to VF at 0.016 megapascal times 0.5 minus 0.016 into 10 to the power 3, and from here H5 is equals to 232.176 kilojoule per kg. Okay. Similarly H6 is equals to HF at 0.5 megapascal, which is nothing but 640.09 kilojoule per kg, and H7 minus H6 is equals to Vf at 0.5 megapascal times 10 minus 0.5 into 10 to the power 3, which will give you H7 is equals to 650.46925 kilojoule per kg. Okay, so now what is net power? Net power is W turbine minus WP1 minus WP2. Okay, so what is W turbine? Okay, so you look at here, turbine work is from 1 to 2 and from 2 to 3. Okay, turbine work is from 1 to 2 and 2 to 3. So from 1 to 3 the mass flow rate was m dot, and from 2 to 3 the mass flow rate was m dot minus x dot. So Wt, now Wt is what? M dot times h1 minus h2 plus m dot minus x dot times h2 minus h3. Yes or no? Then WP1 for the pump 1, the mass flow rate is m dot minus x dot, and the enthalpy change is from 5 to 4. Yes or no? So this we will get it as WP1 is m dot minus x dot times h5 minus h4. Okay, and similarly my WP2 will be nothing but m dot times h7 minus h6. Okay, so therefore my net power will be equal to Wt, that is m dot times h1 minus h2 plus m dot minus x dot times h2 minus h3 minus m dot minus x dot times h5 minus h4 minus m dot times h7 minus h6. Okay, now let me write this one. And what is the net power? Net power is 150 into 10 to the power 3 if I will write this one in terms of kilowatt. Okay, so m dot times h1 minus h2 minus h7 plus h6 plus m dot minus x dot times h2 minus h3 minus h5 plus h4. Okay, so from here we know all the h values, but we don't know what is m dot and x dot. Okay, so one equation and two unknowns are there. So this is equation number 1. Now we need to find a relation between m dot and x dot, then only this equation can be solved. Okay, so what we can do, let us look at the feed water heater. Okay, open feed water heater. So from here, what is the point that is coming in the feed water heater? That is the entry point is 2. Yes or no? And how much mass is coming? X dot. Okay, so x dot mass is coming, and this is my point 2. Okay, and from this side, that is from the condenser, from the pump, m dot minus x dot is coming, and point number 5 is coming. Okay, that entry point is point number 5, and mass is coming m dot minus x dot. Okay, and what is going out? Going out is m dot mass, and what is the point? The exit point is 6. The exit point is 6. Okay, so now we can write an energy balance for this open feed water heater, that x dot into H2 plus m dot minus x dot into H5 is equals to m dot into H6. Okay, so x dot into H2 minus H5 is equals to m dot into H6 minus H5. Okay, so from here x dot is nothing but m dot times H6 minus H5 divided by H2 minus H5. Okay, so this is your equation number 2. Now put this equation here. 150 into 10 to the power 3, that will be equal to m dot into H1 minus, okay, I can include this thing also, m dot, all the m dots together, m dot into H1 minus H2 minus H7 plus H6 plus H2 minus H3 minus H3 minus H5 minus H5 plus H4, then minus x dot into H2 minus H3 minus H5 plus H4. Okay, so H1 H2 H2 gone, so 150 into 10 to the power 3, that will be equal to m dot into H1 minus H3 minus H5 plus H4, and this x dot, now I can write this one as m dot times H6 minus H5 by H2 minus H5 times H2 minus H3 minus H5 plus H4. Okay, so this m, I can take this m out and I can write it here. Okay, from here you can calculate the mass flow rate. 115 to 10 to the power 3, so let me check this one. H1 minus H3, H1 3375.1 H1 minus H3. Okay, so H3 is minus 2150.5033, H1 minus H3 minus H5, and what is H5? H5 is 232.176 plus H5 plus H4, and what is H4? H4 is 231.67. okay, so it is 1224.0907, so it is 1224.0907. okay, minus sign is there already, so H2 minus H3, H2 2642.69995, H2 minus H3 2150.5033, H2 minus H3 minus H5 minus 232.176 minus H5 plus H4, and that H4 is 231.67. okay, so this one into H6 minus H5, H6 640.09, H6 minus H5 is 232.176 divided by H2 minus H5. What is H2? H2 is 2642.6995 minus h2 minus h5, and that h5 is 232.176, okay, and that is minus 83.20 minus 83.2048, okay, and from here our m dot is 150 into 10 to the power 3 by 122.4.0907 minus 83.2048, so that is your 131.476 kg per second. So this is the mass flow rate of the steam. Okay, mass flow rate of the steam. Okay, next is you need to calculate the thermal efficiency of the cycle. Okay, so eta thermal is equals to what? 1 minus q2 by q1, or also I can write this one as w net by q1. Okay, w net is given to us. I just need to calculate q1. So what is my q1? Q1 is nothing but q1 is nothing but m dot times h1 minus h7. q1 is nothing but m dot times h1 minus h7, okay, and so what is m dot? M dot is 131.476. what is h1? H1 is 3375.1, 3375.1, and h7 is 650.469225, 650.469225. okay, so this one will be 3375.1 minus 650.469225, okay, so this will be 358.22355 into 10 to the power 3 kilowatt, okay, so therefore eta thermal is equals to w net by q1, and w net is what? 150 into 10 to the power 3, 150 into 10 to the power 3 divided by 358.22355 into 10 to the power 3, okay, 150 by 358.22355, so that is your 41.87%, okay. So basically we have studied different ways to improve the efficiency of Rankine cycle. So the first way was to superheat the steam at turbine inlet, okay, so but this has got restrictions, is that it, although it increases the efficiency and the quality of the steam at the turbine exit, but the drawback is that the material consideration, okay, so this may hamper the material of the turbine, okay. And then second thing is that to not to by superheating, okay, and by increasing the boiler pressure, okay, so this can also increase the efficiency of the Rankine cycle, but what we have find out that the quality of the steam at the exit is not good, which will result in the erosion of the turbine blades, okay. Then ideal reheat cycle. So we can, what we can do, we can extract some amount and then we can again reheat to some low level, we can extract at some low level pressure, and then again we reheat to the inlet temperature of the turbine. It will also increase the efficiency, but again this has got some limitations. So then the fourth one is the regenerative cycles. Okay, so these are the different ways by which we can increase the efficiency of the Rankine cycle. Okay, so with this I will stop today's class, and hope to see you in the next class. Okay.